Class, today we will study some more topics regarding DFT, among which the first topic would be matrix method of solving DFT. As the definition, the equation for DFT is capital X of k equals to summation n going from 0 to capital N minus 1 x of n Wn to the power small k and small n, where k goes from 0 to capital N minus 1. Now, if we expand this equation and write it in terms of matrix, so in the left hand side we will get capital X of 0, x of 1. In this way we will get up till x of n minus 1. Then on the other hand, we will have a matrix containing the small x's, small x of n's, that is small x of 0, small x of 1. In this way we will go up to small x of n minus 1. So now if we break the twiddle factors varying the k and n, we get another matrix. The components of the matrix can be explained if we take into account that k is varying vertically, that is column wise, row wise, and n is varying column wise. That means in the first component n is 0 and k is also 0. If both n and k are 0, that means you have Wn to the power 0, that is 1. Then in the next column, n is 1, k is fixed at 0. So you have Wn to the power, k is 1, n is 0, that means Wn to the power 0, that is again 1. So all the elements of the first row is 1. Similarly, all the elements of the first column will also be 1. Now, the second component of the second column will be Wn to the power, k is fixed at 1, n is also 1. That means Wn to the power 1. Similarly, the second component of the third column will be Wn to the power, k is fixed at 1, n is 2. So you have Wn to the power 2. In this way, if we calculate all the components in terms of twiddle factor, the last component would be Wn to the power, k is now n minus 1 as well as n is also n minus 1. So you have Wn to the power n minus 1 whole square. This matrix, as we can notice, is a n into n matrix and is called the dimension matrix. So whenever we are asked to find DFT of a sequence, we are already given the small x of n's. So if we can find out the dimension matrix, we can easily find out the DFT of the sequence. We will be solving DFT of a sequence by the matrix method later as we proceed with the topic. The next topic is circulant matrix. We have studied so far 3 different ways or methods of solving circular convolution. The first method was graphical method. The second was the trick method, which is usually done when we want to get notice of any error or to recheck our answer. The third procedure was taking into consideration or utilizing the convolution property. That is, by finding the individual DFTs, then multiplying them, and then finding their inverse DFT. This is the fourth method wherein we use the property of circulant matrix. Now, YCN is written as G of n encircled, which is the symbol of circular convolution. So Gn circular convolved with Hn. Previously, for linear convolution, the symbol was a star mark. Here, the symbol of circular convolution is n within a circle. So its formula will be summation m going from 0 to capital N minus 1 G of m h of n minus m modulus n. We cannot miss the modulus n whenever there is a shift. So now if we want to find y of 0, we have to fix n at 0 and vary m from 0 to n minus 1. So the first term is g of 0, h of 0 plus when m is 1, we have g of n, h of minus 1 modulus n. Now argument of h is minus 1, which is out of our range of vision. So we bring into play the modulus. We add the modulus n. So we have g of 1 into h of n minus 1. Similarly, the third component will be g of 2, where m is changed to 2 and h of minus 2 modulus n. So it is again out of our vision. So we make g of 2 h of n minus 2. In this way, if we proceed, the last term would be where m is equal to capital N minus 1, that is g of n minus 1 h of 1. Similarly, if we now change n at 1, then we have y of 1 is equal to g0 h1 plus g1 h0 plus g2 h of n minus 1. In this way, the last term would be g of n minus 1 h of 2. So in this way, we can also find out y of 2, y of 3 dot dot. The last term would be y of n minus 1. So if we denote these equations in terms of matrix, we will have the matrix that is written here. That is y of 0, y of 1 up till y of n minus 1 will be equal to a matrix containing the impulse functions multiplied by g of 0, g of 1 up till g of n minus 1. Here in the matrix where we have put all the impulse functions or impulse responses, not impulse function but impulse responses, then we see a circular, or the impulse responses move in a circular motion. The first row is h of 0, h of n minus 1, h of n minus 2 dot dot h of 1. The second, the last term h of 1 has come to the first component of the second row. That is h of 1 and h0 has shifted to the second component of the second row. In this way, you see there is a circular motion or circular shift of the impulse responses all throughout the matrix. The last term is h of 0. That means the h of 0 has shifted diagonally. This matrix is called the circulant matrix. So if we are asked to find the circular convolution of two sequences, we will be given g of n, which we can arrange in a matrix, and then if we can circularly shift the other h, which can be the impulse response or any signal, which can be either an impulse response or any signal, y, z, anything, y is usually taken as the output of a system. So if not y, any other term can define the second signal. If it is h of n, usually we consider it as an impulse response. If it is not h of n, it can be any signal. And if we can shift the other signal in a circulant manner, and we can design this circulant matrix, we can easily find the circular convolution. So class, we will leave the video or stop the video here, and in the next class we will start from where we have left. Thank you.